Welcome to this presentation. My name is Leonardo, and I will give you an overview of one of our recent courses at Wolfram U that is focused on electrical engineering. A little bit about me. As I mentioned, my name is Leonardo, and I'm a PhD in electrical engineering. I'm part of the system modeler team, where I work developing the model compiler used when running simulation models. But independently of my work at System Modeler, I have a hobby where I design circuits for music technology. For example, for music synthesizers, which are these kind of machines that are used to make electronic music. During the last year, I had the opportunity to combine my interests in electronics, simulations, and teaching in order to create this new course. The name of the course is Introduction to Electric Circuits, and you can find it at the Wolfram U site. Here you can see the link. This course consists of 26 lessons that make a total of 4 hours and a half. We included exercises, quizzes, and a final exam. But the most important characteristic is that we use Wolfram technologies in order to make the course interactive and provide a nice platform to experiment with the circuits using system modeler simulations. And here's the link, and you can register and start taking the course at your own pace. And when you open the course, you will see this framework that is used for the courses, where you can find all the lessons here. You will have a video, and you will also get the notes for each of the lessons, including some bibliography and also the exercises. This presentation is split into 2 parts. First, we will see a quick overview of the course, and then I will show you how I use the tools to create it. But first, why should we learn electronics? In modern days, we are surrounded by electronic devices, and we all carry some kind of computing device, like a phone or a laptop. And in order to design these devices, we need electrical engineering. And the field of electrical engineering is roughly divided into 2 main parts: digital electronics, which has to do with microprocessors, GPUs, logic devices, and analog electronics, which is the main devices are like amplifiers, power converters, filters. And one of the differences is how these 2 domains represent the information. In the digital world, everything is represented with binary. So we can use voltages, 2 voltages to represent a logic 0 or a logic 1, which can be 0 volts to represent a 0, 5 volts or something else to represent a 1. But in the analog domain, the information can take any value. So it can be, for example, any voltage between 0 to 5 to represent a temperature that's coming from a sensor. And we're more used to see microprocessors as like the most important part in a device. But if just by taking a look at this is a motherboard, we can see that it has a lot of analog components, apart from the CPU and other processors. And the role of all these analog components could be, for example, power management, which is giving energy to all the different subsystems that the computer has. It can also help us to interface with the real world, for example, to produce audio signals. And the role of analog electronics is also to adjust the levels of signals, or doing signal conditioning in order to read information from sensors. And one big advantage of analog electronics is that it can be used in high-speed controllers, because analog electronics is quite fast compared to digital. So this course focuses on analog electronics. Specifically, the objective is being able to analyze and design circuits with operational amplifiers, which we call for short op-amps. Op-amps are these integrated circuits that can help us perform additions, multiplications, subtractions, even integration using voltages. And we can combine these blocks made with operational amplifiers in order to create more complex systems, for example, filters, controllers, amplifiers, or analog computers. In this picture, you can see like two applications that I like. Here we have a picture of my modular synthesizer, which has many modules that I have designed. And these modules are a combination of many analog components and a few digital parts. And on the right, we have another application, which is an analog computer, which gives us like basic blocks that we can connect together in order to perform a simulation, like to simulate differential equations. The structure of the course is split in 4 parts, where we go from the basics to our final objective, which is learning operational amplifiers. In the first part, we try to explain, without going into details, how a simple electric circuit works. For example, here we have a circuit that consists of 3 main components: a capacitor, a resistor, and a voltage source. So the capacitors it's a kind of device that stores energy, and a power supply or a voltage source, it's a component that provides energy, and the resistor, it's a component that allows us to control the flow of energy. We can see this as for example, charging the battery of our phone, where we can connect our phone to the power outlet using a wire, and then energy from the voltage source is being transferred to the capacitor. So this is a simulation model that we created in System Modeler. And in order to have an idea on how this circuit behaves, we can combine it with this kind of interactive simulations. Here we can see in the bottom the simulation results. In blue, we can see the voltage of the capacitor, which represents the energy that is stored. So in the beginning of this simulation, the capacitor is discharged, and then the energy from the voltage source is being transferred to the capacitor. And it has to go through the resistor, which is going to define how fast or how much energy it is flowing. And with this interactive simulation, we can explore what happens. For example, if I increase the value of the resistor, okay, if we increase the value of the resistor, the capacitor starts charging slower. On the contrary, if I decrease it, it will charge faster. If I change the value of the capacitor, and I make a larger capacitor, I use a larger capacitor, it will take longer to charge. So, and this is basically what we learn in the first lesson, or in the first part of the course, like just having this idea on how one of these circuits can work. The second part, which is basic theoretical concepts, we learn the physical definitions of things like current, voltage, resistance, and power. These concepts are very important because they provide the mathematical models that will help us understand the behavior of circuits. Then we go into the third part, in which we cover the methods for the analysis of circuits. When we start creating circuits using multiple components, it gets progressively difficult to obtain the design equations. Therefore, we need a systematic approach to analyze them. For that, we learn methods like the mesh analysis and nodal analysis, which allow us to take a circuit like this and define the equations that describe the behavior of this circuit. So based on those methods, following the rules, we can obtain a set of equations like this. And then we can just use the functions from the Wolfram language in order to solve the system and obtain like a formula. Like in this case, what's the voltage of this node based on the values of all the components that we see here, and also in the values of the resistors and the voltages. When the circuits contain other components like capacitors and inductors, we need to describe them using differential equations. In the section of analysis, we also learn a few techniques to simplify the analysis, for example, using the Laplace transform. When using the Laplace transform, this technique allows us to see the circuits in a different way. For example, we can see how a circuit behaves in terms of frequency rather than time. If we take as example this simple circuit that has one capacitor and one inductor, we can follow the techniques that we learned in this lesson in order to get like this transfer function. And once we get the transfer function, we can start calculating, defining formulas to calculate what are the values of the components that will give us the response that we want. And we can see, for example, how it will behave for different parameters. And based on this, we can decide what's going to be the values of each of the components. And as mentioned before, the fourth part is operational amplifiers. And as I mentioned before, operational amplifiers are integrated circuits that allow us to perform operations using voltages. Here we can see 4 different circuits in which we use the operational amplifier. Here you can see it on each. And just by changing the components that we surrounded, just changing the connections, we can make it perform different operations. In this case, we have an addition, and just by changing the components, we can get a subtraction, we can get comparisons, and by adding a capacitor, we can get an integrator. And there are like a bunch of configurations that we can create. And during this part, we learn all these configurations, and we also learn how to calculate how to calculate the values of the components and make this circuit behaves the way we want. And once we know how to design and calculate simple operations like additions and integrations, we can start putting them together to create more complex systems. For example, in the course, one of my favorite applications is, as I mentioned, music technology. So many of the examples have to do with sound generation. And here we can see a circuit of a voltage controlled oscillator, which is basically a circuit that generates sound waves. And it uses 3 operational amplifiers. And we can hear and we can actually simulate the circuit and hear how it will sound. I want to show you the sound, but I have to unplug my headphones so you can listen to it. Here we have what's the sound of a triangle wave. It may be a little bit low for you because it doesn't have too many harmonics. But now let's hear a square wave. And this is a pulse wave. And finally, a sawtooth. And all these waves are being generated by this circuit. And the next thing that we can create, once we have a sound generator, we need like a way of shaping the sound. For that, we can use a voltage control filter. And this is the circuit that we analyze, which consists of different subsystems. We have 2 integrators, a subtractor, and also like a kind of mixer to control the signals. And when we put together the sound waves that we generate, and we pass them through the filter, and we modify a little bit the parameters, we can get very interesting sounds. For example, this one. Or just by changing the parameters, we can get like different sound. And if we can continue like creating these kind of systems, we can develop other blocks that are used in synthesizers. For example, here we have a diagram where I put the voltage control oscillator that we listened before, the filter, a voltage control amplifier, and a few modulators like a low frequency oscillator and an envelope. And then I put together also a sequencer, which is just like the notes that are going to be played. And when I simulate this model, I can get the results and listen to the music that this circuit creates. I'm going to play it for you. that's like a basic baseline that is entirely simulated in System Modeler. Okay, so all this, I took all these circuits that we saw before and I built them using real components. In these pictures, we can see the resistors, capacitors, and other integrated circuits. Then I wire them together in order to put some panels, and then I can mount them in this rack where I can start connecting all the modules together and also make music with it. I'm going to show you a snippet of a video that I recorded where we can listen to some of the sounds that I created using this system. And that's basically the whole course. Now I would like to show you how I use System Modeler and the Wolfram language to create the interactive notebooks. So all the diagrams that we saw were created in System Modeler. This is the synthesizer diagram that we saw before, and I can enter inside of these blocks, and I can see the electric components that I use and also other subsystems. For example, the core of the oscillator, which was this part. So basically, this block, it's a dual oscillator. It's the one that you saw in the video that I use. This is the filter that I showed before, and we can see all the electric components, the operational amplifier models, etc. This is a voltage controlled amplifier. The envelope generator. So the nice thing is that when we create this kind of diagrams, we can simulate them and create on top of them the interactive panels. For example, if I take this simple circuit, which is the one that I showed in the previous slide, and I simulate it, it is possible to define a plot within System Modeler and also define using these explore panels sliders that will help us to change the parameters of the components. So I can do exactly what I was doing before, like changing components and see what's the impact on the simulation, and starting doing experiments with it. And once I have this panel created, using a simple command, I can replicate all that behavior into a manipulate within the Wolfram, within a notebook, and that's exactly the same panel and experiment that I designed in System Modeler, just taken back to the notebook. And as I mentioned before as well, it is possible to simulate a model. This is what I'm doing here, and after that I can take the simulation results and create an audio object which will play back the sound. And this is the sound that I played before, this like sequence of notes. There is also another nice thing, which we can obtain equations out of the systems. For example, here I have a very small circuit where I can get all the equations with a command. And these are the equations that describe the whole system. And then using some of the Wolfram language features, for example, to solve these equations and obtain like these long formulas that is the complete solution for our circuits based on symbols. And from here I can replace some values in order to get like some nice formulas that describe the circuit. So here's again the link to the course. You should be able to find it if you search in your favorite search engine, Introduction to Electric Circuits, Wolfram. And as I mentioned before, it is about 4 hours and a half of videos. There is also a study group available. Here's the link. And in this study group, we went through all the lessons and we had Q&A sessions. And all these sessions are recorded and they are about like 10 hours of video. And that's the end of my presentation. If you have any questions, please let me know. Okay, so I have a question here. Does a student for this course needs a system modeler license to take the course? So I think that when you can request, you don't need it. You only need it if you want to modify the circuits, but you can take the course and just follow all the lessons, but you will not be able of editing the models. And if you want to take the course, you can actually get a trial license that will allow you to modify the exercises and just make whatever you want with it. I have another question that is there such a thing as a field programmable integrated circuit with multiple analog circuits that can be connected together like an FPGA, but for analog circuits? I don't think that there isn't anything commercial, but there is a course. There is a. I saw like one university in the US. I don't remember which one, where they were making this kind of device. I saw it in a YouTube video, but I think that it's not commercial yet. Hopefully, at some point, it's going to be available and it's going to be possible to have such kind of technology. So it's like a way. It's like a way of having a bunch of analog components and being able to reconnect them without having to do like I did with a bunch of wires. So I have another question. Where is the circuitry where's your circuitry where you are choosing the notes being played by your synthesizer? Okay, so in that case, it's not exactly a circuitry. It's a modelica model. So if you can see here, I have this sequencer object, and what I'm doing is I'm selecting voltage values to define the nodes, and gates, which is just when the node should be on or off. So this is basically my sequencer, and this one sends the voltages that the modules we are going to take, and is going to produce the music. I have another question. Is there any advantage of using system modeler rather than SPICE for simulated simple analog electric circuits? So, I mean, there are like two different kinds of simulators. SPICE is quite good at simulating like in more detail the semiconductors. So when you add a transistor or a diode, they have like more advanced models. So you are going to get like let's say a more precise result, but at the same time it will be slower. If you see these models that I made, they have a lot of components, and specifically the models for the operational amplifiers that I use are very, very simple, and these are behavioral models. This means that instead of simulating every transistor that the circuit has, I replace them with a model that behaves similarly to the component, but it's not that complicated. That allows me to do like much faster simulations. So I think that that's one of the biggest advantages of system modeler. When you don't have a model for something, you can create a behavioral model and easily like make your own library of components and use it in simulations. I think I have answered all the questions. So, okay, if there are no more questions, we can end the session. Thank you very much for attending and enjoy the rest of the conference.